Talk about friction. So we know that friction is there in everyday life, and so it's a good idea to understand how friction works. But friction is actually passive force, which means it acts only when there is an active force present. For example, let's say if you have a table and there is a mass situated on the table. So if you're being asked what is the force of friction acting on it right now, your answer will be, well, think about it. The force of friction acting on this guy right now is 0. Why? Because there is no active force acting on it. Well, active force in which direction? You can say you have an x direction and you have a y direction. So in which direction? Well, active force along the direction in which the surface is. So friction always acts along the surface. So this is the surface, and along the surface you do not have any active force acting. But let's change the situation. We still have that mass, but now we apply a very small force, let's say 0.2 Newton. And now if you're being asked what is the force of friction on it right now, well, it's 0.2 Newton. Why? Because the guy is not moving, because we applied this small force, and because of this force is being counteracted by the frictional force, the net force acting on the mass is 0. And because the net force is 0, there is no acceleration or motion. There is no acceleration in the system, and there is no motion in the system because of that, and the guy just sits there. Okay, let's increase it even further. So you might have seen it if you have a book lying on the table, and if you apply a force, you will see the book will not move if you apply a small force. But if you keep increasing the force, what happens? After a while the book starts moving, right? So let's say instead you have this book here, instead you apply a 1 Newton force, and let's say even for 1 Newton the book is not moving. Then if you draw a free body diagram of the book, it should be like this, which means the net sum of forces is 0, and because it's 0, the book is not moving or is not accelerating from its at rest position. Alright, if we keep on increasing, we expect, so if we draw this on a graph, let's say this is how you are applying the force, and this is how friction is acting. So if you keep increasing the force, the active force, the force of friction also increases correspondingly, which means for the same F you have the same FR. F and FR are the same, just in the opposite direction. But this is not going to happen for any value of F. You will see that if you keep increasing F, after a while friction is going to give up, and the book is going to start moving. Well, what happens? The friction really cannot go above a certain value. So it keeps on increasing as you increase the active force, but after a while it hits a threshold somewhere here, and this is the maximum value of the friction. So now let's see what are the different factors which decide or affect the maximum friction force. So this is Fr max. Okay, so let's invoke two arguments. The first argument is, if we make the table surface rougher. So if we make the surface of the table rougher, what do we expect? We expect that the maximum friction force is going to, let's say this was the original one, then we expect that this should be the graph for a rougher case, right? You see, the maximum friction has gone up because the friction is rougher. You have to apply more active force to get the book moving. Okay, so friction depends on the roughness of the two surfaces which are in contact. What else? Let's say if on top of the book you apply let's say you put one more book. That's a good option. Let's put one more book here. Then would you take a larger force to move both of them when you apply it? Yes, you will require a larger force to move this set of two books, and then you will see that actually if this is the original, then the new will be something like this. So what is the variable that is acting here? Well, the variable acting here is the normal reaction, how hard the two surfaces are pressing against each other. If they are pressing hard against each other, then friction is more, and if they are not really pressing hard against each other, then friction is less. So we have seen the friction depends on how rough the surface is first, and second is how hard the two surfaces are pressing against each other. So the maximum friction force people have found out experimentally is mu n, where mu is called coefficient of static friction and n is the normal reaction. Mu is a representation about the roughness of the two surfaces, and n is the representation of how hard the two surfaces are pressing against each other. If n is large, that means the surfaces are pressing each other a lot. Similarly, if mu is less, which means the two surfaces are smoother, then the coefficient of static friction is less. But keep in mind, this is the maximum friction force. Friction force, maximum value of friction force it can achieve. What people make mistakes is that they assume friction to be always this number. No, friction is not always this number. Friction is only that value which keeps the body from moving. But if you keep increasing the active force, the friction also keeps increasing, and it reaches this maximum value, and it really cannot go beyond that. So this was all about static friction when the object is at rest and then it breaks off. But what happens, let's move on to the next step, but what happens if you keep applying the force and the body breaks off? So it starts moving now. So just before moving, the force of friction acting is mu n. Let's put a subscript s to differentiate the two cases. What is s? S means static, which means body is not moving. But as the body starts moving, you see there is some sort of smoothness that comes between the two surfaces. Rubbing causes smoothness. So if you rub your hand, the surface becomes smooth. So now the maximum friction force is no more mu s times n, but is actually mu k times n. I'm not sure whether the coefficient, the subscript is k or not, but it looks like, if I remember correctly, the subscript is k. And this is called coefficient of kinetic friction. And you will easily understand that mu s should be greater than mu k. Why? Because this force is greater than this force. So n is same in both the cases, but because of smoothness caused by the motion, friction has gone down, and so the only logical conclusion you can draw is that mu s should be greater than mu k. And if you draw this, compare that to what we have been drawing. This is what we drew. Instead, what happens? The object goes up to here. I mean, the force of friction goes up to here, but as the object breaks off, you see it breaks off somewhere here, because friction really cannot oppose the active force. The force of friction goes down. Why goes down? Because in this region is force of friction takes a value mu k for the coefficient of friction, and in this region it is still mu s, right? But the static friction can be anything between here and here for value of f, but kinetic friction is always constant, which is, so kinetic friction is always mu k f. Why? Because you see object is already moving and friction is acting to its fullest to make sure it counteracts the active force, so it's always mu k f. But a static friction, it behaves like this. Okay, so this is all about friction, and in the next lecture we'll talk about some examples on friction.